Another week, another episode of COMP2300 series. Thanks for joining, folks. I see a few people have logged in already. Great to have you watching on YouTube or Twitch. Just making sure I've got everything ready before I press go. Got a good lecture today on memory and memory operations, which hopefully will clear up a few things. This is an exciting time in COMP2300. In this early few weeks of the course, where we're really covering things that you've taken for granted in other subjects. Like last week, just being able to add two numbers together, you take that for granted. In week 1 and week 2, being able to run an instruction, you've taken for granted. And this week, taking for granted the idea of storing things in memory on your computer. But we're going to work out how it works today. Make sure I'm getting everything on Teams. Teams should be good to go as well. Where is my Teams? Where's my team? Oh, I wonder what hard questions someone is going to ask me today. I better flick through my slides and see that I remember how to do everything. That should work. Someone's giving me a thumbs up for that small comment. I gotta get my remote control-y stuff working as well. Okay, we'll start in a minute. Make sure I know what's going on the team. Everyone's there. Yeah, there's people there. Right-hand side small is what I want. And I'm going to actually start my recording. G'day folks, welcome to COMP2300, Week 3, Lecture 1. Memory operations. Thank you so much for joining me today. Thank you for everyone who's tuning in live across the nation, live across the world actually. And thank you also to everyone who's tuning in not live, who's watching this on YouTube as a recorded program and on Echo 360 at the ANU. I was just checking that I am actually appearing in this video. I can see that I am, so that means that everything is going well. I know that my streaming is streaming and my recording is recording. I do like to do a recording here just in case there's any issues with the internet, which has happened before. Today's topic is memory operations. As I was just saying before in my pre-show banter, memory operations are something which we take for granted when we're doing high-level programming. We take for granted this idea that when we say x equals 10, then later on when we want to use x, say y equals x plus 1, y will equal 11, because the value 10 that we put into that variable x is remembered somehow using memory of some sort, and later on it is recalled. But this week we're going to go into a little bit more detail about how that works on your microbit and in computers in general, and talk about some of the nitty-gritty difficulties about memory that we have to understand in order to really understand what happens when you say x equals 1 in a high-level programming language. Just as a small admin corner for today, I'd like to remind everybody to have a look at the assessments page and recall that the lab tasks, the first group of lab tasks is actually due at the end of this week, or in a more correct sense at the start of next week. I want to give you as much time as possible to review your lab tasks, make sure that everything is just as you want it. You've completed all of the tasks that you want to, and you've had a chance to revise things if anything is bothering you. So I've set the due date for the lab tasks to be the last possible moment before labs begin next week, which is 8 o'clock, 0800, 8 a.m. Canberra time on Tuesday, 15th of March. Monday, 14th of March is actually a public holiday here in Canberra, so we're not putting a due date on that day, even for just the lab tasks. So just make sure you revise this page, have a look at your lab tasks. For many of you, you will just be doing the tasks in the lab, and that's all the time you need, but I would encourage you, if you miss something, go back and check it out. I know we had some issues with the CI jobs not completing, and we always want to see those little ticks on our CI jobs when we're checking something off. But I think that's been solved for this week, so whenever you are contributing or doing your week 3 labs, then you will find that the CI jobs work just fine, and when they rerun, you'll see all the little ticks for all of the little lab tasks that you've completed so far. And just for clarity, if you're seeing ticks, you've made a decent attempt at every lab task. That's what I want you to do. It doesn't need to be the absolute best solution in the universe. These are quite basic tasks from our perspective of the course. They're just something that I want everyone to be able to complete, or everyone to be able to have a good attempt at. So just taking some code that is a reasonable solution for those tasks and putting it in the task file is all I'm asking you to do. We're not putting a deadline on a public holiday. Actually, I think it's ANU policy that we don't have deadlines on public holidays. So if another lecturer, don't quote me on this, but if another lecturer starts putting a deadline on a public holiday and you don't like it, then tell them about that. There's many things in the ANU assessment policy which are, I guess, important information about how the rules for assessment, and I think that there are often things related to assessment that is framed in business days, and a public holiday not being a business day is obviously kind of no-go for deadlines. Anyway, I always put deadlines on not public holidays, either last thing on a Friday or first thing on Monday morning. I just don't want people to be working on their holiday if they don't have to. I know people stress about assessments and do it at the last minute, but there you go. Although I guess you will work on the public holiday if I put it first thing Tuesday. So maybe I'm not so nice after all. That's all for assessment. Another, just keeping your eyes on the prize as we go forward. Lab tasks, first lab pack due at the end of this week. Next week there'll be a quiz available on Wattle. I'll have that set up and ready to go this week. You'll start to see it appearing. In week 5, well, next week we'll also release the first assignment, so you can start to have a look at that. Week 5, you'll have to create a proposal for the assignment, or a design proposal for your assignment task. You can read about that in assignment pre-submissions. I'll talk more about it next week. And then actually assignment 1 will be due at the end of week 6. So the first big assessment task for this course is the first assignment with 20%. So that's a significant chunk of marks, and I think everyone's going to want to spend a good chunk of time on that to make sure that they get a really great assignment submission. But it should be a lot of fun, I think, so don't freak out. Let's do the lecture. Getting to the lecture. Memory operations. Unfortunately, the first thing we do in this lecture is not a memory operation. It's a little bit of a different topic, but just completing the last little bits of our ALU lecture. Probably I should move these slides to the week 2 slides, and if I teach this next year, I can do them in week 2 instead. But one thing to recall when we're talking about memory in COMP2300 with the microbit is that memory is the way that the CPU interacts with everything else in the world. It's not just storing information, it's all kinds of interactions that aren't basic arithmetic happen through memory. So learning to use memory operations is absolutely core knowledge in this course. You will need it all the time, starting today. So look at this lecture, read the notes, learn them really carefully, get a really good idea about how memory operations work. You will need them throughout the rest of this course. The reason is that we've got this thing called the memory map, where there's a bunch of stuff mapped into memory locations that you might not expect. And if you look at this memory map, I'm just going to breeze over this now because we come back to it later today. This section down the bottom says code. There's a bunch of memory space dedicated to code. There's a bunch of just regular memory, SRAM. Here's a bunch of stuff called peripherals. That's all of the devices that are attached to your disco board. All of these things are related to all of the devices that are connected to the MCU on your microbit. And as someone has just said in the chat, it's about I/O. Memory operations are used in I/O for the microbit, or a general thing for all systems. Look, I'm not going to make general points about all systems, but very, very frequently memory is used for input-output on systems. Electron memory ought to be unforgettable. I don't have a... so I think I just said disco board, sorry. Someone said unforgettable. I need to have like a dub siren, boo boo boo, when I say that. Yeah, so there's a lot of stuff in the memory map, the whole completely addressable range of memory, which is not remembering things. It's connections to other kinds of devices, which does happen on your disco board and also happens more generally in other types of CPUs. First, a few more instructions. This is stuff which I guess is related to the ALU week, but you may have started to guess some of these things already. That will be useful. We've looked at some instructions for adding together, subtracting, multiplying, and dividing numbers so far. But I want to introduce a few more instructions which are related to bits, to logical operations between bits in a register. So in all of the arithmetic instructions, we treated the register as containing a number, either a signed number or an unsigned number, or it doesn't matter, both at the same time. But there are other instructions, for instance, the AND instruction, which is just doing an AND operation between each bit in a register. So for instance, if you've got a register which is wrong color, I need it to default to green or red, 01, I need to get someone to hack on my Jekyll code so I can get this to work. If you take those two bit two registers, suppose we're only using 4-bit registers and we want to AND them together, then we AND those two together, we get 0, we AND these, we get 0, we AND these, we get 1, we AND those, we get 0. So it's treating each bit in the register separately as a separate individual binary number and ANDing them together. The OR instruction is doing the same thing except with OR, doing a logical OR with each matching set of bits between the two vectors. There are a couple of other clever instructions called compare and test, which don't actually calculate a result. They don't have any output register. All they do is set flags, which will become important later on when we talk about conditionals in your assembly programs. So I'm just going to show you the bit operations section of the cheat sheet now, resources, the assembly, ARM assembly cheat sheet. These ones are right here, shifts, we're skipping that for now. Oh, I don't want that. Arithmetic, logic and tests, here we go, sorry, looking at the wrong ones. Logic and tests, so here's the logical operations, and, or not, BIC, which is interesting, we'll show you that in a minute, and then ones that, and exclusive OR, and then versions of these that have an immediate instead. Whoops. Someone's started talking about some cool stuff in COMP2300. I don't know anything about COMP2300, but what I do know is that in first year computing, there's always some smarty pants students who know about bit operations already and they do something clever. And I'm still puzzled remembering back to my first year computing where I could kind of get what they were doing, but I don't quite. So if you don't get it yet, now's a good time to learn it. And don't feel bad that you didn't get it in first year, because I didn't get it in first year. So, I don't know. Don't know what to say. Clever kids knowing bit operations already. These test ones we're not going to worry too much about right now, because they don't have an output. We're only worried about output ones to, right at this moment. We'll get back to the ARM assembly cheat sheet a bit later. But the one which we have to think about is this BIC one, I think, because we haven't talked about that. The other ones are a bit more clear. Exclusive or, and, or not, I guess, is a little bit self-explanatory, but BIC is very useful. Here's an example of BIC, and BIC doesn't stand for a pen or for a lighter or for a pencil. It stands for, or a safety razor, it stands for Bitwise Clear. So it's useful when you want to, if you've got a register full of bits and you'd like some of those bits to go away, you use Bitwise Clear. So what it does is any bit that's set in your second operation, your second operand, I suppose, those bits are going to get cleared in the first operand. So here the first operand is FF, which is going to be 1, 1, 1, 1, 1, 1, 1, 1. Second operand is 1, 0, 1, 0, 1, 0, 1, 0. Oops. And when we BIC those two together, this one, that one's a 0, so that's going to do nothing. The 1 goes straight through. That one's a 1, so that one's going to get cleared. The 0 goes straight through. That one gets cleared. 0, so that one goes through. That one gets cleared. 0, that goes straight through. And that one gets cleared. So we've kind of, it's like a raise operation. In a similar way, OR is kind of a adding operation, because if you've got two registers, for instance, 1, 0, 0, 0, 1, 0, 0, 0, and you OR it with something that just has a 1 in it, it will only add the ones. The zeros do nothing, so 0, 0, 0, 1, 1 or 1 is 1, 0, 0, 1. So OR is kind of like adding bits, and BIC is kind of like subtracting bits, but not subtracting them in a numerical way, sort of a more obvious bit by bit way. how's this thing implemented? It's ANDing it with the inverse of the second operand. So if we have a look at this example we just did, the inverse of the second operand is going to be 01, 01, 01, 01. Now that's a 1, so we get the 1 coming through. Anything that's turned into a 0, because it previously was a 1, ANDing with a 0 is always going to wipe out what was there before. So that'll be a 0, that one goes straight through, 1, 0, etc. So it works. It's R1 and not R2 in this example. You can see the example on the slide. It's just very spread out. I thought it would be more fun just to draw it in. Another little section of the cheat sheet which we have to go over before we go any further and forget where we are. Bit shifts and bit rotations. So this is another thing which is particularly useful if you're thinking about a register as being just a bunch of bits, a list of bits or a vector of bits, not a particular number. We'll just have a look on the slide. Sorry for blasting you with a big white website here. Moves and shifts. The moves we already know about. The shifts are shifting a bit vector along. So there's a couple of interesting ones here. LSL, LSR, ASR, ROR, and then the same with immediate values. And then there's weird one, RRX, which is a funny one. Oh yeah, there's an explanation. There's a more clear explanation down the bottom about what these things do. And here's also an explanation right here. Sorry about the lack of contrast at the left-hand side here, but I think everything else is possible to see. This is logical shift left. So what it's going to do is take whatever you've got, whatever your bits are, and push it to the left in your register and insert zeros at the right side. So let's just have a go. I'd just like to know what this does on a microbit. MOV, 0, OX 1010. 1011, that's a bit nicer one. LSL, R0, R0, 3. I hope it compiles. Yeah, it did. Phew. Okay, I'll just load that number in here. I made it a hex number. I meant to make it a binary number. I knew I was doing something wrong. So there we've got down I just have to hover my mouse there and I can't point to it, but you can see the right end of the binary digit there is 1011. And now I'm going to shift it to the left 3 places. And we've still got 1011, but there's 3 zeros to the right of it. So we've pushed that number along in the register. What happens to the numbers at the end here? Well, the very previous one, whatever was in bit 31, is going to end up in the carry bit at the end. Anything else just gets thrown away. So they all fall into the shadow realm. Oh no, I'm falling into this is my kind of whirlpool of badness. Any bits that go off the end go into nothing, the void, lost for eternity. Logical shift right. We're doing the same thing except the other way. So we can, if we shift by 3 bits in this example, it'll put 3 zeros in on the right hand side of the register at the high end, and it will, whatever was the last thing to be shifted off the edge gets kept in the carry bit. And we can try that one too. Let's do, because we've got 1011 there, if I shift right 4 places, we'll have something in the carry bit. So logical shift right, R0, R0, 4. Okay, if you remember, that's where we were. The last byte was 01011000, and now we've got 00000101, and the carry bit is 1. And we didn't have to put, or maybe I needed to put Lazarus or something for it to actually work, but let's put some S's in there. And LSRS, the carry bit is 1. And it was changed from a 0 to 1 that time. I think the previous time it was 1, it had already been a 1, and I hadn't overwritten it with anything. Cool. All right, next one, arithmetic shift right. So this one is these ones are cool when you've got, if you've just got bits and not interpreting them as numbers, you've got bits in there for some reason, which will be very useful in later weeks. Then shifting them around is very handy. You just want to put one bit into the 24th spot. You could say mov 0, 1, and then LSL 0, 0, 24. That'll move something to the 24th bit, one single bit into the 24th bit. That's very handy. But it's also handy to use these bit shifting operations to multiply and divide numbers. The only limitation is that you can only multiply and divide by 2. So you can, if you shift a number, suppose you get the unsigned number 1, and you LSL that by 1 place, LSL mov, now this same one, LSL, there's no comma there, R0, R0, 1, then you'll now have at the end of the last byte, you'll have 000010, so it'll be 2. So we've just multiplied it by 2 by shifting it 1 time. If we shift it 2 times, we'll end up here. So it's 4. Shift it 3 times, we get to 8. And so on and so forth. So whatever number you put in there and you LSL it, you're going to get a number which is multiplied by 2 to the power of something, k, which is the number of things you've LSL'd it. 0 times 2 to the power of k. It's the same as going LSL R0, R0, k being a immediate variable. Immediate what is it? Immediate value, yeah. So that's so far so good for things that we are multiplying by 2, but can we divide by 2 as well? You can shift to the right, and you're going to be dividing by 2 each time. So you can use LSR to divide a number by 2. I'm going to prove it to you by doing something here. So we'll say, let this one equal, 12 in decimal, and we want to multiply it by 8. What's 8 times 12? You can tell me that in a minute. I remember what it is now. So we get LSL S, I'll keep the S there, R0, R0, 3. So I'll turn this to decimal mode. We've got 12 there. Cool, so far so good. And we multiply it by 8, and it's now 96. That's handy. Now we're going to divide by 16, and we get 6. It's going to drop something off though, so it's doing our a division of whole numbers and not giving us the remainder. The remainder's dropped off the end. So, oh no, it is exactly 12 times 96. 6 times 16 is 96, isn't it? Is that right? Yeah. So far, so good. There's a really good question there for Julian. So I'm going to let Julian answer that about using bit operations being faster for bit maps. I think Julian we're talking in the chat about how bit shifting operations can be faster, have very high performance in high-level languages compared with, for instance, an object-based representation. So if you've made classes and objects for a certain situation, then you're doing a lot of complicated operations with that. If it's possible to treat all of your representation of something as bit vectors and do it all with logical operations, you can cut a lot of overhead in your code. So when it compiles down to implement all of those objects and operations and classes, it uses a lot of assembly instructions to do that, and uses a lot of different bits of memory to create the overhead. But if you're just using kind of binary representations in variables, they can often go straight into a register, just have a few CPU instructions to do the maths with it that you need, and be much quicker. Okay, where was I here? Well, so far so good, but if we're going to have problems if we have a minus number, if we're in 2's complement land, because then, suppose that was minus 12 in fact. I don't know why it doesn't work with a pound sign there, but if we have minus 12, actually the shift left does work. That's taken it to negative 192. So far so good. That's great. So the shifting left works because we started out with minus 12, which had a huge number of ones at the start of it, and then a few zeros. Then we shifted left, and we've just pushed everything to the left, got some zeros there. But when we shift right, logical shift right, we should be back at minus 12. So we just logical shift left by 4 places, then logical shift right by 4 places. We should have cancelled them out, right? But it hasn't worked that way because we've shifted in a bunch of zeros on the left-hand side. So when you're dealing with 2's complement numbers, you can't, or 2's complement interpretation, you can't do the logical shift right and expect that to do division. But you can use the arithmetic shift right, and all that does is copy whatever the last bit is. If that's a 1, it copies it into the empty spots. So it's just that if you have a number which is negative in 2's complement implementation, it will always have a 1 in bit 31, and it's just copying that 1 in all the n number of times that you're doing. So we can check that this works. ASRS. So we should be negative 12 multiplying by 16, dividing by 16 should equal negative 12 again. Negative 12 multiplied by 16 is negative 192. Divide by 16 is negative 12 again. Hooray! The live might have been paused. Sometimes the MS streams don't work very well. Sorry about that. You know, from my house here, I stream to, I've got a good bit rate, so it's good at my end. Sorry. I stream to 3 different services. I stream to Twitch, I stream to YouTube, and I switch to MS Streams. The MS Streams one is regularly the worst. It doesn't work as well as I would hope. And that's a pain. I'm sorry about that. So there's 2 questions have come up which are really important. The first one is from someone who says, how does the CPU know to display the numbers as negative? Sorry, when I answer a question, I try not to use people's name. So I'm sorry, I am talking to someone in the chat who's asked this good question. I just you haven't given me permission to put your name on a public stream, so I guess I try to avoid it. I know on our internal team system just inside the ANU, I'd be okay using people's names, but not so much on the public internet. How does the CPU know how to display the numbers as negative? Do you mean this display, that says -12, that's not the CPU knowing, it's VS Code, in fact is the Cortex debug extension of VS Code, which is working out what's in each register, and it's just in this decimal mode. There's two number modes, one is hex mode and the other is natural mode. And in natural mode, it just assumes that anything in a register is a 2's complement number. So it will always display it as -12 if it's got a lot of ones, I think. Second question, yeah, and so I guess the real answer for that question is the CPU still doesn't know if things are negative or positive numbers. It doesn't know. It's up to you as the programmer to know. Someone says that ASR seems always to be a better choice than LSR. It's not if you're not using 2's complement numbers, in which case you would never use ASR. And it's from almost all of the things you will shift for, you're not using it to divide and multiply. You'll have to trust me on that, but there's a lot of times in this course where you need to get a bit or a pattern of bits into a particular part of a register, and you're going to use the shifts to do that. You don't need to use the arithmetic shift so much. If I wanted you to divide, you'd probably just use the divide instructions. Some of those actually end up using shifts anyway, so that's beyond scope here. Someone's saying, oh no, we have to encode floats ourselves if we wanted to do them in ASM. Yep, yep, you would. That's why, you know, math.h exists or, you know, environments for compiling code have extensive mathematics built into them, so we don't have to do it ourselves. They're mentioning, this is still talking about the floats, things are automatically rounded down. Well, they're just dropping off, we're just cutting numbers. I mean, it's a kind of division which is not high precision. I think I might save an example for the Piazza for that one. So it is doing some, I hesitate to say rounding, it's just not considering remainder, it's only considering the integer division. I think I've answered those questions. I want to move on to the next bit, so see what's on the next slide. Oh, look, we've got two more. I haven't even talked about these two. I'm not going to do examples for these two because they're easy. The rotate one, rotate right, is actually copying whatever you're shifting off the end into the other side. So rather than shifting and dropping things into the shadow realm, we're saving whatever is on the end and putting it at the top. So that's handy for some reasons. Then RRX is another similar kind of rotate. It's rotation with extension. Rotate right with extension. And the extension is the carry bit. So the carry bit is treated as an extra part of your number there, and that ends up on the end first. So if we just shift by rotate right with extension by 1 bit, whatever's in bit 0 goes into carry. Carry goes into bit 31. So it's kind of like a 33-bit rotation. If someone can work out a reason to do that, tell me about it, because I haven't had any reason ever to use RRX. Now, there's a thing we talked about last week about how we could use this, how we could represent immediates in assembly. And I talked about this idea that you have this 12-bit immediate field, usually, inside a instruction encoding, and then you can, the CPU can rotate that field to give you a very large variety of interesting numbers, useful numbers, I suppose. But we can also use this, this method to do some useful shifting and rotation inside a single instruction. So you can, for free, get multiplication when you're doing some addition in one instruction still. It's not doing anything extra. It's got extra hardware in the CPU to do more executing than you would typically need it for. So an example is that you can you can add two numbers together and also left shift, logical left shift, one of those by 4 places. So you're adding R2 with R1, except R1 has this LSL applied to it. So it's multiplying R1 by 32 times 32. And that opens up a lot of interesting possibilities for doing very substantially reduced number of instructions for certain operations. We'll just have a look at those here. You see it's got this idea for shifting. Add can always be shifted, RM, and there's the shifted bit there. And all of these shifts are documented down here. It's a little bit hard from the cheat sheet to kind of get the picture about what you're supposed to do, but you can see it here on the slide. There's the normal instruction. You simply add a comma, and then the type of shift you want, and then the number. Oh, sorry, multiply by 32, I meant 16. Whoops. There's a course rep in the chat telling me how wrong I am. Don't I know my 2 times tables? Obviously not. Here's an example, mov R3 4. Actually, I'm just going to copy it in. Not draw, copy. I'll copy it onto my microbit and we'll see how it works. Whoops. Oh well, didn't work. Oh yeah. Just copied about a million slides there. Okay, we're back. Sorry, I will run this example. I swear we're going to get to some stuff about memory today. We will get to it. 4 is in R3 now. That's so far so good. We're going to just do a multiplication by 4 with the mov instruction, which seems like an odd choice for multiplying, but okay. If we just want to multiply by 4, divide by 4. We get 1, and that one, divide by 3, divide by 8, except it's pushing things off the end when we start dividing too much. There's a slightly different, slightly weird behavior, right? It's rounding down to 0, so it's because it's interdivision. 1 divided by 8 is 0. Off the end. We'll look at the bits this time. Look at the bits. So I've got 0100. Now I'm going to mov R3, logical shift right by 3 places. We get 0001 in the last 4 bits, I mean. Then we'll just keep rotating it off the edge, and that 1 has disappeared into nothingness. What's the point of mov R3 in practice, lol? Well, there's a very good point, I think. If I look at the ARM assembly cheat sheet, arithmetic. If you want to do multiplying 2 numbers together in ARM, I think you only have a register version of mul. So if you've got a number in a register and you want to multiply it by 2, you could use the mul instruction. But to use that, you have to put an immediate value into another register. You have to have a free register that you're not using for everything else. You have to spend an instruction cycle moving an immediate into that register, and then you have to run the mul. So 3 things. Free register, move a thing into that register, run the mul. And if you don't have a free register, you might have to spend other instructions clearing something out of a register to access it. Or you could use mov R3 LSL1, which would multiply that number by 2 in 1 instruction with no free registers, and you don't have to spend any time doing anything else. That's actually pretty good, right? It is actually pretty useful. It's not, it looks stupid, right? It looks stupid, but it's you know, stupid like a fox. It's a little bit smarter than it seems, these special Lizzle operations. In practice, you laugh now, but you might be laughing on the other side of your face in an assignment when you're using them all the time. Good one to remember. Try out these shifts. Don't just let them sit there. If you're doing some mulls and it's just by a power of 2, try using a shift to do it. Just see if you can. Just challenge yourself. All right, is that everything in our cheat sheet? Well, it's everything for the moment. We haven't looked at everything in the cheat sheet. Someone's going to tell me I'm wrong in a minute. Yeah, well, they're not. They're agreeing with me. So at least you think I'm right at the moment. I'll accept that. We haven't looked at everything on the cheat sheet quite yet. And the cheat sheet has a lot less than the reference manual. You should have opened the reference manual at least once by now. But you can do a lot with the basics, and these are the things that I expect you to be practicing in your labs, trying out different ideas, and you can refer to the cheat sheet whenever you need it. Someone's claiming that you do still need a free register. No, you don't, because I only have used one register here. This was the number I wanted to multiply. What I want to do is 4 times 2, for instance. Okay, so if my choices are MOV R3 4, I've always got to have one register. If I want to multiply, I'm going to have to put MOV R4 2 and then do mul R3 R4. So I've had to use that register. Or I could get rid of these and just do MOV R3 R3 LSL 1. We got live updates to Revealify to make the default pen red. Thanks, Julian. I'd love the red pen. Is it a good idea to reserve a register for these kind of operations? Then, in the case MOV RN and RN can't save you, no, it's not a good idea to reserve registers. If you need them, you need them. But when you have memory, you can clear registers by pushing them off into memory, which we'll talk about soon. Don't worry too much about being I don't know. Don't be parsimonious with your registers. Like we do have quite a few, but what tends to happen is you want to go and run a function or something which does stuff with your registers that you can't remember. And if your function is long, it's hard to remember which registers are going to be messed up. And we tend to have some rules about which registers are allowed to be messed up by a function, which have to be saved and restored. We'll get to that stuff. How do you keep track of all your registers in your program? What if you run out? Oh, but this is what we're talking about now. How are you going to keep track of these registers? How would you even know if one was your safe register, your saved register for emergencies? Only crack open in case of emergency, that register. And what do you do if you run out? So I suppose I've blown it already by saying you could use memory, which I said at the start, and I said last week, and I say every week. But you give me some thoughts in the chat, folks. Jump in. Tell me how do you know which registers you're using for certain things? I probably shouldn't pull down the updates that Julian has put into the website to make during a lecture. That would probably be a bad thing to do. Oh, you could write it down somewhere. I suppose you could be... This is the important register for containing 4. You have some rules, I suppose so. You could say MOV R6, OX, 1002. Don't erase. Have some rules about my registers. I think, I guess one of the points I'd like to make here is that it's going to be hard to implement rules like that and make them work. Because as soon as you go down the page and you can't see that rule anymore, it'll be a little bit hard to keep track of it. So really, when you're dealing with registers, you tend to not use them for too long in a program. Like I was talking about the high-level programming situation of saying let x equal 10, and then later on at any time in the future you would hope that you can recall x and it would still equal 10. If you said x plus 1, it's going to be 11. But that's usually not a great assumption to make when you're doing assembly programming, because it's hard to remember what registers are for. You tend not to use them for too long. Memory addresses. We'll get to this. So why would I need to use memory? Why would I need to use memory? Registers can store data. We can just live in registers forever. We can live with registers. So they certainly can store data. We've been using all of these instructions to store data in our registers. They should be, we could just say that one is X, it's going to contain 10, and that's just the way it's going to be. And registers are in fact super convenient. They're very close to the CPU. They're built into the CPU. They're inside it. And we can give them all special names. You know, you've got your 16 registers. And some of them, one of them is R0, oh great, R0, R9. And we've got R6, of course, which is our special don't erase register that we're saving for emergencies. Don't erase me. And we've got these other mysterious LR and PC, which is very useful for our program working, the fetch, decode, execute cycle. Well, how much data have we got here? Including LR, SP, and PC, we've got 16 registers. So that's 16 times 4 bytes. How many bytes is that? 4 bytes. So we got 64 bytes. That's a lot of data to remember. I think probably we're going to need more than 64 bytes just for doing normal computation. So we might need to store more data than it's possible to store with registers. I don't think anybody ever said that 64 bytes were enough for anybody. There's a famous quote. I think it's often attributed to Bill Gates making some point about 64 kbytes of memory, kilobytes being enough for anybody, which was probably taken out of context really, but it just goes to show how silly these things seem in hindsight. 40 years later, right, the amount of memory he was talking about is just a rounding error on memory technology now. But the cool thing about the registers, they're very small, but they've got little nice names. We can give them all a name and have special purposes. It's like having a pet duckling, right? We could have a little family of ducks for COMP2300. We could have mummy duck and the 5 baby ducks. And one of them would be called Jeffrey, and one of them would be called, Kylie, and one of them would be called Julian, I suppose. Could be a ducky. Julian's out there doing something for me. And we could say, look, I don't mind erasing Jeffrey and Kylie, but I'm not going to erase Julian. If we only have 5 little duckies and mummy duck, then we can give them all names and have a special purpose. Oh, there's 6 duckies here. Sorry, I misspoke. 6 ANU duckies. There's a special ANU ducky back there. Heidi duck. Yeah, the ducky slide's a good one. Yes, our little duckies each have a purpose. If you're on campus, you'll see that we've got some lovely ducks here on ANU campus they're kind of our pets. They're a wild animal, but we love them as part of our wild natural environment. Then not a lot of them have names, because once you just go beyond one family of ducks, there's a lot of ducks to have to name, and we can't just refer to them by individual names and expect to remember, and we certainly can't remember things about their personality. So if we're thinking about our registers, each of them has a nice name, and some of them have special personalities like PC, which is used for a specific purpose, and of course don't erase R6. That's the special one we're keeping in case of emergency, an emergency multiplication situation. So registers are like our little pet duckies. I'll get to the next bit in a moment. What about memory technologies? So I think intuitively when I talk about memory, you're thinking it's a place on your computer where you're storing data. And mostly we have this this three-letter acronym, a TLA, RAM, Random Access Memory, RAM, for what our memory is. RAM, my computer's got 32 gigabytes of RAM. RAM is useful. We can use it for storing information that's bigger than a few bytes. 4 bytes can fit in one register. So things that would take up more than that, like the character data for a game, or the pixel data for a photo, or the machine code instructions for a large program. You'll need more than one register, or even a couple of registers to store that information. So it's good we have RAM. And it's not very expensive now to have a large amount of RAM compared to what your microboard, I almost said disco board again, your microbit has. I just had a look today, and if you want 16 gigabytes of RAM for your desktop computer, that's going to cost you about 100 Australian dollary dues. 100 Australian dollars. That's not very much, really. 100 bucks. It's a couple of hours work for most people. Quite affordable for quite a lot of memory, 16 gigabytes. Well, what makes RAM? What makes this memory? We're not an electronics engineering class, so we're not going to go into great detail about how you create memory. But I need you to remember that there are 3 technologies to keep in mind when thinking about memory. One of these technologies we've already talked about. We've talked about flip-flops, using the components of logic gates to create a latched circuit, which will hold a single bit. And that's often, when it's used in a memory array of memory, it's often called static RAM or SRAM. It's called static RAM because it will stick in the same place, just like we talked about. It's latched. Until you decide to change that RAM, it will stay latched as long as the circuit is powered. That's the kind of memory which is used in your registers, SRAM. It's used in lots of kinds of memory which are close to the CPU. There's usually a kind of memory called cache, which is right on the die next to your CPU, so it's very close to your CPU, but there's more of it. Then there's another very popular memory technology called dynamic RAM. Dynamic RAM is typically what's used in your computer when you're talking about the number of gigabytes of RAM you have. That's the dynamic RAM. It's called dynamic because it actually forgets the data if it's not constantly reminded. So it's very forgetful RAM, but it's quite cheap, and you can fit a lot more bits into a certain amount of space. So it's physically dense, so it's good for high capacities of RAM, and it's more power efficient. So is it cache or cache, someone's asked. I'm not going to be drawn on that. Yeah, Julian is saying that there was the quote about 64K of memory being enough for anyone. I think it's a misquote. It's probably not Steve Jobs. Steve Jobs, no, it's probably not Bill Gates saying that, but it makes a good story. No matter what you say, 16 gigabytes, 32 gigabytes is a good amount of RAM forever. Well, call back in 10 years when everyone's got a terabyte of DRAM in their computer. DRAM, there's some interesting comments coming in here. I'm going to address some of those in a minute, sorry. We haven't got to the third type yet. We'll just finish the second one. It's called dynamic because it's forgetful. The circuit needs to keep reminding it what bit it's containing, keep refreshing the value. Different than the static RAM flip-flops, which once they're set, they're latched. They'll remember as long as the circuit is powered up. Both static RAM and dynamic RAM, flip-flops and DRAM, both of those technologies forget what they've remembered when you turn the power off, okay? But there must be some kind of memory which doesn't, and we call that non-volatile memory. So it's not going to forget what it's trying to remember when you turn the power of your computer off. And the technologies for that is usually, the main technology we have these days is called flash. It's a non-volatile memory technology. So it's used for storage that you need to be permanent, your SSD for instance, and it's usually denser again and a little also slower again than dynamic RAM. So your computer might have, well, mine has 32 gigabytes of RAM here. I've got a nice little desktop here for doing my streaming, and I've got, I think, about a terabyte, 1,000 gigabytes of flash storage. different drives connected in different ways. When I say more complicated to read-write to, I think I might just specify what I mean. When you're in static RAM mode, you can have it wired directly in the CPU, call it, give it a name like R0 and recall just that byte, just that word of information, or just one byte of it. Dynamic RAM, again, you can often just recall one byte of it at a time. But for flash, sometimes it's a bit more complicated, where if you have to write, you can't just write 32 bits at a time. You might have to write a whole bunch of it at once for the circuit to work. They often call a bigger group of memory a page. So I think sometimes in some flash technologies, a page is 4 kilobytes. So you have to have quite a lot of that memory stored in your DRAM or in your cache on your CPU, and then change what you need to do there, and then write the whole page back to write it to your SSD. And most computers have all three types. But normally when you say RAM, like how much RAM does your desktop computer have, that's just DRAM. And we use other words for the other kinds of memory, like we usually call this one storage space, or how much hard drive space have you got. And the first one would be how much cache is in your CPU. So different CPUs, some that are more expensive might have more cache space. Usually all CPUs of a certain platform have the same amount of registers though, and not that many of them. The question here was, is the CPU cache versus RAM on this RAM on sticks what languages usually refer to as stack or heap memory? No, that's not a difference between stack. That's not what the difference is between stack and heap. We will get to stack and we will not get to heap. Heap is something which is a bit more. It's a concept which is not as easy to get to with assembly programming. Stack we can definitely get to, and we definitely need that kind of memory. On the subject, why does Google Chrome tend to use a lot of RAM? I don't know, ask a Chrome programmer. 4K of RAM sent humanity to the moon. It did indeed. So you can do a lot with a small amount of memory. What about on your microbit? How much RAM do we have here? Well, we got 16 general purpose registers, 64 bytes, a whole 64 bytes of register memory. We've got 128 kilobytes of RAM, and we've got 512 kilobytes of flash. We've got a whole half a megabyte of flash. So we could contain probably one image from the COMP2300 website in flash with some left over. Maybe two if it's a small image. We could have 2 images in there. So this is a bit small compared to your laptop desktop, but your microbit doesn't need a lot of memory for the kinds of programs it's designed to run. There's people in the team talking about Chrome using a lot of memory. That's exciting. So this is where we look at, there's a lot of further reading slides in this week. I wanted to point out a few things here. One is this website, which is related to shift and rotate instructions. It's some lectures on ARM at Cambridge. Mentioning again Ben Eater talking about how memory works. And then the first appearance of this book, Essentials of Computer Organization and Architecture. This book is actually in the ANU library. You can read it online. If you go and search for it in the library, you'll be able to read it. This is the online version on O'Reilly.com, and you can read that book. One funny thing about it is that the author's last name is Null, so it looks like they've made some kind of error in putting the data of the book in, but it's just their name. So it's a good book. It's the book that I refer to when putting together a lecture for this course. I don't speak about everything in that book. This course has a distinct flavor, but that book is a good reference for most of the topics. If you want to know about memory, just go have a look at that book and read a chapter and see what you learn. Now, back to the baby ducks. Back to the baby ducks. If we had zoomed out on ANU campus and we looked at all of the baby ducks, there's a baby duck flapping away with its wings. This one might be, Jeffrey. And this one over here, whoops, that's Kylie. But we've got a lot more duckies, and I'm not going to be able to invent names for all of them. So we're going to need some other way to refer to to these different birds. And the same thing happens in your microbit and in your big computer, because your memory of your big computer is just going to be absolutely chock full of zeros and ones, and you don't even know where things start and stop. So how do I know what this data is? Is this supposed to be a number, right? This random grouping of 32 bits, or is it supposed to be this one? Is that one the number? Is this one a string, right, down to here? Or is this one my MMORPG character? I don't know. There's a lot of places where your data could be. We're going to need to have some way to figure out where it should be. So the solution here is to refer to each section of memory with a numbered address. And each of these addressable things is called a cell. So each memory cell will have one address so that you can get it out. And you can think of this like a big array for your memory. So we could be storing some numbers, 80, 65, 54, a bunch of extra numbers in an array called memory. And then if I want the number to get that number 80 back, I can just do memory 0. If I want to get this one, I can do memory 2. Just the same, we're just having an address. The index of an array is very similar to an address. And it's similar to the way that we remember where places are in the world, right? We might have a sequence of houses down the road. This might be, there's a church there, so I'm going to call that Church Street. And the church might be called 0 Church Street. This is 1 Church Street. That's 2 Church Street, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then they run out. That one's 13. This is on the, sometimes you skip one if it's like, oh, maybe this one's 10, it's an empty block, that's 12. So just the same as a street where we're putting numbers that increase over time. Of course, when we're on our microbit, our numbers are not going to be in decimal format, they'll be 32-bit binary numbers, unsigned numbers. Turing Street should be nearby. Probably Turing Street's this one, with a little pool at the start. Turing Street. So now we've got some addresses, and we start at 0 all the way up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And each of these addresses refers to 1 byte. Whoops. That's kind of a byte, yeah. This is not an exact representation, but each address is not, it's not referring to a single bit. We're just going to take a byte to have one address. Now, where are we next? You can think of each of these bytes as being a little spot to store some data, a little bucket. The size of our bucket for storing data is 8 bits, 1 byte. And each of these buckets is going to be numbered. 0, 1, 2, 3, 4, 5. They could just be plastic containers. They could be cardboard boxes. It doesn't matter. Any kind of way of kind of dividing the borders between little chunks of data so that we're not living like this where we don't know the difference between any zeros and ones. We've got them in little easily digested, easily divided arrangements. So the byte in your memory system, and in most memory systems, is the smallest addressable unit. We often say it's byte addressable. One interesting thing, should it be smaller than that, maybe we could have a 1 bit in each bucket, or 8 bits, or we could have it as 16 bits in each bucket, or a 32, 167. It's a good question, and it's something which is decided when someone's designing a CPU and the memory addressing system, but it's very typical to have 8-bit byte addressing. Most systems you will ever see will have 8-bit byte addressing. It would be either a very old or a very obscure system indeed if it doesn't use 8-bit byte addressing. In fact, there are older, I mean really, seriously antique computers like the old mainframe era, where 1 byte might not mean 8 bits, it might mean a different number. You can read more about this in this Wikipedia article, about what different sizes there were. They might be used for addressing. So why 8 bits to a byte? No fundamental reason. People have settled on that as a good number. It also, typically it's handy that you can store an English language character in 8 bits. It gives you 256 different values, so you can store all of the ASCII characters, which is a bit of an American or English-speaking focus on the world. Where are the ASCII characters? Well, they're all here in different ways. There's a bunch of weird characters that are used for controlling a terminal. Then all of the letters, the uppercase letters, lowercase letters, and the punctuation. There they all are. That's all of the ASCII characters. So this is one of those moments where the way that computers are designed suits English-speaking Western culture and is not so convenient for other cultures in the world. And it's a kind of consequence of colonialism that's the case. This is assumed to be the best way to store information, and thus it is so for everyone. Of course, there are other technologies newer for storing all kinds of character sets and making extensible ones. But this, you can see, it's dated 1977. It's from a time when people didn't really think about these didn't worry about what the rest of the world would think. Now, back to addresses. A memory address. A memory address is just a number, and it refers to a particular byte in the memory space of your system, your computer system. When we were drawing these sequences of memory, the memory is really an array, right? But we tend to draw it in 2D sometimes, or we kind of go from 0 to F, maybe 16 bytes across, and then go down this way. 0, 1, 2, 3, etc. That's just one way of doing it. You could go backwards, you could go upwards, you go downwards. It's a 1D array, so there's lots of ways of representing an array to make it more easy to understand or visualize. Now, a question for everyone. With the instructions we've already covered in this course, are you going to be able to access memory and store to it as well? Give me an answer in the chat, and I'll sip my coffee. Or I'll take a step back for a minute and let you think about it without my face. We use the mov command. Someone say we use the mov command to store in memory. No, we use the mov command to store in registers. I guess registers are a kind of memory, so you're correct in that. Mov R0, that puts something into this register, and it can only deal with registers, R1 all the way up to PC. No, we need to store in our memory that is not registers, we need another kind of command. Nope, we need another kind of command. They're called the load store instructions. I've missed a couple of good questions here. Sometimes my my Teams doesn't update very quickly, or it's gotten stuck on something. Oh, registers are memory, that's true. Okay, well, I'm wrong. Ooh, I think some people have worked it out, that there are ways to we've seen letter, but we haven't seen store. A few questions. You have a few suggestions. You have actually used like .data and .hword, and that will store things in memory. But it only stores in memory at compile time. You can't do it at runtime. .word, again, that will put a OX, dead beef. That'll store some arbitrary bytes in your program memory if it's in a text section, or in RAM if it's in a data section, but it won't. That'll go to RAM. That'll go to flash. Well, they both go to flash, but this one ultimately ends up in RAM. We've got a couple of instructions for dealing with memory. You've already had a look at the LITR, load register instruction, in your lab. So we're going to start with that one. So you'll see how it works first, but it's going to point to your assembly cheat sheet. Close the arithmetic section. Open up loads and stores. We've got all these ones. Oh, they're complicated, aren't they? There's a few words. Stack, we said that word stack before. It will show up eventually in your instructions, but not right now. The first and two important ones for today is just load register and store register. So this one loads something in memory into that register. This one stores something in a register into a place in memory. So this loads some data into R0, and the data is located in memory at the address defined by R1. When you use this command, it's not affecting the memory. It just loads it from memory, copies it out. It doesn't change what's in memory. They're still there after you run LITR. You're not going to delete them. Whoop. So, what's with this thing? There's been a few questions, good questions on Piazza already about some of these weird LDR instructions and what they might do. Whenever you see a register name inside square brackets, that means it's an address in memory. So R1, that's the location in memory addressed by value in R1. The location in memory addressed by the value in R1. Folks, it is a critical point of your system's low-level computer understanding to keep a very good idea in your mind, a very good mental model of the difference between data in memory and an address that refers to memory. An address and the data in the memory. So these two things, sometimes in a higher level programming language, they get associated because you sometimes pass around the address as if it's a value, when it's actually just the address of something in memory. But it's something to really think about today, that you're talking about addresses and places in memory. The data lives in the memory, the address refers to it. And these memory addresses, they're just numbers. They're nothing special. There are numbers from 0 to FFFF. Julian is asking, I think he was saving this hard question for the lecture. The question is, I saw in my assembly LITR, my disassembly, this command, LITR R1 PC, comma, #8. We haven't even run one single LITR command yet, but I'm going to show you this one. This is an interesting one. This means load into R1 the location in memory addressed by whatever is in PC, that's a register, you can access it, offset by 8, so left shifted, or adding eight places to it. So it's not shifted, it's just adding. If we look in the cheat sheet, you can see LITR RD in brackets RB, comma, constant is defined to be RB plus constant is the address, and that's get the memory addressed by RB plus constant. So this means load the memory addressed by PC plus 8 into R1. The word in memory. So it literally loads a whole word from memory, 32 bits or 4 bytes. So in fact, you start at an address and you go 3 extra. And this is a weird one because it's seemingly going to load a word from our code into memory, which is absolutely what it's going to do. It will load whatever is at PC, which is going to be pointing to here, that instruction, plus 8 bytes, which is going to be 4 instructions. And it will load the next 2 instructions probably into R1. R1 is sort of dereferencing R1. Oh, we're not using the dereferencing word terminology. That's a C terminology. But you're absolutely right. Yeah, that's inside the brackets is the address, and outside the brackets is sort of the memory addressed by that address. Whenever you see those brackets, think this is a memory address. I'm loading the memory referred to by that memory address. Let's do some examples before Julian asks me any more hard questions. Addresses and immediate values. Can we specify the memory address in an immediate value? Sure can, but you can't fit every memory address in the world into an instruction encoding, because you have to remember that MOV only has this 12-bit immediate, and the addresses are 32 bits. So there's some addresses which aren't going to work in the 12 bits, even with all of those tricks about rotates and shifts and everything. More often, you'll read the address, you'll have the address from a register, and you'll read them in that manner. You get the full 2 to the power of 32 possible addresses there. So typically you get your address into a register and then you read it into the register, reads the address into the memory you want. So here's a typical thing we do. Whoops. I'll delete all this stuff so far. MOV 0 hashtag OX20001234, and then I'm going to letter R1 R0. So I'm putting the address, typical pattern you'll see, put the address into R0, and then load R0 into R1. Let's see what happens with this program. I think I know what it's going to do, which is not very much. We'll load, oops, get to natural numbers. We've got this number in R0, and now we're going to load that into R1, and I get a bunch of junk. A bunch of stuff that I haven't put there and didn't want to know about. So just loading memory is not very useful. We also want to store from memory. Oh, I already did the demo. Convert a slide. Oh, what? I want to do the storing. I'm going to skip. Ooh, one offset. The question was, if it's PC addressing, does one offset correspond to exactly one line instruction? No, because each assembly instruction is 16 bytes. 16 bits. Narrow ones are 16 bits. That's 2 bytes. So 2 bytes is typically one line, unless it's a wide instruction, in which it's 4 bytes. So, like writing this. This was the question: was what do I do? Can I just get exactly the next instruction? Maybe it's going to be, well, this is going to get you the next instruction because PC is the next instruction. Letter PC #2 #2 is probably the next instruction down, maybe, but typically you would not do this by hand. Don't write this in by hand. Use the assembler to help you. I'll show you some examples, I think, next week with that kind of stuff. Calculate offsets from PC. Someone's asking, is there a chance you'll override some important memory when storing in memory? How do you know what memory is free? Woohoo! That's a loaded question. We could spend weeks talking about how do you know what memory is free. The real answer is you don't. Or you have to just remember what you were using last. Oh, good question. Someone saying, and second question, follow-up question, what if you just start writing in your code memory? Well, your code memory isn't writable. The microbit is smart enough to be able to make sections of memory not writable, and it's set them as read-only. We're going to store first. Store something useful, and then we'll ask some questions. And that's not a real demo, so I'm not going to do that. I'm going to say mov ox200000 is my address, and now I'm going to store something in there. Mov 2, equals 167. I'll use ox0167 as a number. I don't know why I sometimes do a pound sign, sometimes I don't. It doesn't make a difference. Someone asks, is memory default zeros? I think not. I think it's default anything. So if you want it to be 0, you're going to have to set it to be 0. Stir. Store R2 in memory address R0. Oh, unused memory is typically 1s. So there you go. Thanks, Julian. $167, we got that in R2. I want to store it in memory. Did it. And now I want to load it back. I'm going to load it into R1. There's my R1. And we got it, OX167. Cool stuff. So we can store and load. Let's see. View memory. Let's view it in memory. OX21001234 was our address. And I want a length in bytes. I guess I'm going to use like 4 bytes. I just want exactly that much memory. There I go. Now remember this endianness thing. When humans read hexadecimal numbers, we start with the highest value digit. But when computers read hexadecimal, they start with the lowest number digit, typically the lowest byte. So the 67 is going in first, that's the first byte. Then the 01 goes in next. Then we wrote a whole word, store R2, R0 is storing the whole 32 bits, so we need another 2 bytes, which are zeros. So we could do something that uses all 4 bytes in our word. Oops, I broke something here, didn't I? Oh, I can't use that as it's not a value I'm allowed to use. Ah, come on. What's something good? Well, I'll do that later. I'll think of a good number to put in. Invalid constant up to fix up. Error, make error 1. Yeah, so you can't just mov any number into any other into any register. Yeah, sometimes you have to use a different technique to get your address somewhere. So a few questions. Are these valid memory addresses? This one seems okay. This one, 1, 2, 3, 4 bytes, seems okay. -9, I guess it's okay, it's a valid memory address. We'll just be representing it as like 1, 1, 1, 1, 1, a lot of ones, and then maybe a few zeros. Ooh, Julian told me the answer for my previous question. This one over here, 1, 2, 3, 4, 5 bytes. So this one actually is not valid because it's too big. This one's actually right. It's just that the addressing system isn't going to see it as -9. It will see it as a unsigned, whatever its unsigned value in, and be totally happy. Is there a way to automatically assign memory addresses? Really good point from someone in the chat there. Is there a way to automatically assign memory addresses? In fact, maybe what we should do, and just bear with me folks, in fact what we should do maybe is just say, okay, we'll just take some point in memory as our starting point, and then when we store in it, we'll just move along a little bit, and we'll kind of keep a pointer to where we're up to in storing in memory. Does that sound like a good plan? We'll talk about that a bit more later. We'll just give you the answer for these questions. The answers are yes, 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 and no. The only reason this one's no is it's too big. So certainly it's a good number, but it's got too many digits there. So if we have this memory, I'll be in green mode maybe. If we wanted to do this kind of keeping track of our memory, we could say, well, whenever we store in memory, we keep moving up. And then if we wanted to erase something, we could just erase what we had on the top. Whoop, and come down again. In fact, it starts to look like we're using it in our memory. We're kind of making a stack of memory addresses, and we just keep adding to them whenever we store something in memory. And we could kind of keep a pointer up to where we're up to. It could be called the stack pointer in some way, SP. So you might be guessing that I'm leading you down this path of realizing that the register you've got called SP is exactly for keeping track of where you are in one part of memory so that you can make use of it easily during your program. The stack pointer. Yep, someone's asked, how big is too big? Well, too big is more than the address space we have. We only have 32 bits to address in memory. That means our biggest memory address is OXFFFFFFF. Whoops. FS, no, FF. That one's bigger, so we can't use that one. We're not talking about stack pointers today, but it's a very good point that it's annoying to specify an address every time. The other way to specify an address is to use a label. We'll talk a bit more about labels. Something, you know, .word. You've seen that one before, I think, in your labs. .word, blah, or .ASCII, blah. That'll store it in memory, and then you can refer to the label as your place where you're storing it. So we've talked about this last week, but I'll just mention it again. This idea of ARM instructions having at most 12 bits of room for immediate values. You can't represent every single value. You can't represent all 32 inside the immediate value encoding. But instead, we've got 12 bits, so we have an 8-bit immediate and then 4-bit rotation. There's the link to this really nice blog post which explains how that works. We had a look at that last week. Whoa, my tab crashed. Oh, well, I'm not going to do any small things and then load them again in the middle of a lecture. That doesn't seem like a good idea. Firefox is doing something weird. Storing to memory, we've already had a look at this, the str store register instruction. It's kind of the sibling of LDR. Use the value in R1 as the memory address. You remember that bracketing notation. And there's an example, a similar one to what we just used. So, and we spoke about this already as well when we ran our demonstration, the memory is byte addressable, but a register can fit 4 bytes. So when we load something into memory, for instance, I'll just do another example here, 0000 F A, B, C, D. That, I don't know if that's allowed or not. I'll go AA, BB. I'm not sure what the ones are that are allowed and which ones aren't allowed. That one's allowed. So I'm storing my data in memory. Boop, BB, AA, 0000. So it starts with the smallest byte and puts that in memory first, moves 1 byte up in memory, does the next smallest byte, AA, moves up in memory another step, does the next byte, and then moves up in memory again, does the next byte. Now it seems like, it might seem at this stage like, oh gosh, there are a lot of different amounts of data that I have to remember how they work, right? There's bits, there's 32-bit registers. Then last week we were talking about instructions being either a word long, one word is 32 bits in this architecture, or a half word long, 16 bits. And now you're saying that memory is byte addressed. And I guess the point of byte addressing is that that's the one which is common across different computer systems. So the memory in your memory, in RAM, is byte addressed. Your storage is byte addressed. Things you get in from a network will be byte addressed, divided into bytes and arranged that way. So you actually, most of the world is in this way, and there's only a few things which have funky half words related to your CPU. Because often, like, things you want to store in memory are bigger than a byte or bigger than a half word. So you need to use a lot of bytes to store them. I guess the thing with this endianness question, is like, you've got a starting point in your memory and you just have to work out how to fill up the buckets first. And if we had our number OX00 A 0000 AA B B, it could start at this end, start putting that in this bucket, put this byte in this bucket, put this byte in this bucket, that byte in that bucket. It could do that, it just doesn't. That's just not the way it happens. So in fact, we start at the little end first, that's why it's called little endian. And we take the BB, put them in this bucket, take the AA, that one. And I guess in some ways that makes sense when you think about how we deal with numbers frequently. So when we were doing our additions, if we had 0101 plus 0011, we don't start at the big end, do we? We start at the little end. So we do a lot of things in this little end order. 1, 1, 0 carry the 1, 0 carry the 1, 0 carry the 1, and 1. So we do a lot of things in a little endian order as humans with maths, but it just turns out that on this ARM CPU, we also load and store data in little endian manner. Unlike humans, where if I'm writing down a number on the board or in a textbook, I tend to start at the big end first, $1 million. But we can always go back. That's just how it is. Someone says, it is what it is in the chat. That's true, it is what it is. Why do I need to care? You do need to care about endianness because you might have been the person to store that memory, or it might have been read from a file created on another machine. And if it's a different machine that's in big endian mode, it might be switched around. You might have gotten it over a network, in which case you're not quite sure. You have to obey the rules of your certain kind of discussion with another system or certain transfers of data. As it happens, little endian is more common, but there's certainly big endian existing in the world, so it's something to know. More reading about endianness, go have a look at it, particularly this good one, Computer File. A bunch of great computer science teachers who love talking about things related to old computers. Boy, I'm almost almost, well, I'm not quite through my slides, am I? I'm going to stop in a minute and do something else. I've forgotten, don't know what I'm going to do, but it'll be something fun. Load/store half words and bytes. So you don't have to just load a whole word at a time. You can load a half word, just 16 bits, or you can load a byte, just 8 bits. They work exactly the same way. You just have to have a B at the end of your instructions. Stub, stir, and lidrb, and lidr. Just the same thing. These are really useful, particularly in the instance where you don't want to mess up other memory. If you're just reading memory byte by byte, you just want one byte at a time, maybe it's good just to read that byte out. Let's see where I'm going with my talk. A byte half word version is necessary. Could you live without them? Is an address or a number? Questions. Oh, that's it. We'll talk about memory address space in a minute. On Thursday, I suppose. Can you live without these ones? Why is a byte 2 characters in memory? Great question, someone's just asked. Two questions, which are both great. First one I'll ask is this: why is the byte 2 characters in memory? When I've got those 2 characters in memory, I'm actually not writing, I'm writing using hex digits. So the byte could be 8 bits. Oops, that's 9. That's a byte. Now, another way of writing it would be as a number, 100. Or it could be all the numbers between 0 to 255. But often in computers we don't want to talk about decimal numbers because they're not the only way we think about data in computers. We often think about data just as bits or as characters or as something else. So a byte, we tend to just think of it as data that doesn't have an interpretation. So it's often good to consistently use not binary, but hexadecimal, where each of these groups of 4 bits gets turned into 1 character. So what's that 1 character going to be? That's the 8's column, so it's 8 and 2, and it's 11. That means that it's B. And this one is 8 and 4, 12, 13. CD, DB. If we use decimals, another thing is we'd have to go up to three characters, because it would be 0 as the smallest, just 1 character, or 255. So we'd need 3 characters in a go to handle it. But the hexadecimal interpretation is most common when you're displaying just raw data. You tend not to display it as bits because it would take up too much space on a screen. Hexadecimal is quite compact. 4 bits turns into 1 character on the screen, and you can view them that way. So whenever you've got these 4 bits, something like that, OXDB, that tends to just refer to a byte, 1 byte. We're not splitting those up any further. And we're not switching them around either, because it's 1 number being written at 1 time, corresponding to 1 memory address. And it is a little bit confusing that when you've got a word, DBAC0134, that it's getting switched left to right, 01, that's in the register, and then when it's in memory, 3401AC DB, it is confusing that the whole thing is getting switched around, but each individual byte is staying the right way. So you're not turning around your whole characters, you're turning around each pair of characters. It's confusing, I know. Nothing I can do about it, I'm afraid. You just have to keep it in mind, and hopefully it's something that you remember as you're doing your programming and having more experience with these systems. Are the byte half-word versions of the instructions necessary? Could you live without them? I think you could definitely live without them. You could just have to do a lot more instructions, right? You could shift off a bunch of things to clear them out. If you're just using a byte, letter B Let's try this one example. I'm just going to load 1 byte of that from memory. So it should just load BB out of memory. Store it in memory. Okay, and now I'm going to load into R1 the byte, which is at 0, 0, and I get OXBB. So I suppose I could just load the whole word here, and then shift all the way to the right, save my BB, shift them all off, and then shift all the way to the left and just keep that byte. Or I could use letter B to just load and store 1 B at a time. If I just store that single byte, I'm going to ignore everything else in my register and just store the BB. So we'll start again. The memory viewer is just displaying whatever happened to be in memory before I was doing anything, which is something because the memory was used previously. There's a startup program that has to start your code. I store just the B in memory now. Just change the B, cool. And now I load it back and I've got the B loaded back in R1. And I've kept O1, O2, and O3, those offsets in my memory. That's handy. Now, a little bit of a trick here. If you've got data, you know, saved something, .word OX ABCD 1, 2, 3, 4. I've now used the .data directive to store something in my memory, which is actually going to store it at 2000000. See, there it is, A, B, C, D, 1, 2, 3, 4. And I can now retrieve that back with my letter commands. But if I just don't want to deal with writing in the whole address, I can do what Julian suggested that I do earlier, and something which we talked about, I've discussed a little bit on the forum. Someone was asking, what is this thing? Letter R, R0 will have the address, and it's going to be equals save something, that label. This is the way you do it, right? I hope I'm not forgetting it and mixing it up completely. Okay, I want to get the address of this label, which corresponds to that word, in memory. I run this command. There it goes. Now that word happened to be, that address happens to be 2000000, but I don't have to remember it. I can use the label there to help remember it. And then I'm just going to load that value into R1. OX ABCD 1, 2, 3, 4. Now, if we look at the disassembly of this, whoop, I lost, where's my disassembly gone? Ah. Here's that thing that Julian was talking about, that funky offset PC storage thing.
I didn't get that.
Oh, I've got talking to Siri. The reason that that's there is that this letter R0 equals label. It's a handy way of like getting any immediate value into a register, no matter what method has to be used, and the assembler will work out the best method for you to use it. So this is a common thing we see with the equal sign. It's called the letter pseudo instruction. I'll go through it in a bit more detail a bit later, but I just wanted to point out that that's a great way of accessing something without having to type out a long memory address. Any questions right now? I feel like the chat's been pretty quiet for a few minutes. We could do another few slides because I want to have some space on Thursday to talk about other stuff as well. No questions so far. That's good. There were a few questions before. I suppose we answered them. Memory, address, space. Address space? It is like a big universe of addresses out there, isn't it? Lots of different cells of memory, and we're referring to them all with little numbers, just like we refer to stars. What's the point of getting the memory address and not the value itself? Very, very interesting point, Josh. I'm not going to get to these slides because I'm going to talk about this last point as our last thing to talk about. So the question was, and this is a good one. Why would I just get this? Why would I want to get this address into R0 and not just directly access the data there? I suppose I could, because I could put in OX ABCD 1 2 3 4 right there. I'm entering the data in. In memory address space, no one will remember your scream. Very funny. The reality is that to access something in memory, you have to have its address. You can't get it directly unless the address is encoded as an immediate. And the address OX2000 isn't going to be able to be encoded as an immediate in our load register instruction. There's not enough space for an immediate in that instruction to encode the actual address, which is, for this one, the address here equals OX2000. That's too big for a letter immediate. It works for MOV because of the special shifting thing, and works for letter pseudo instruction. If it takes a register to get a register worth of data, why not just store it in the register in the first place and save the hassle? Totally good point. We could just be storing, in this particular program, we could simply be storing this number in a register. This is totally valid. Now we've got that number in a register, and it's saved there. The problem is that we have to have this number in the instruction stream loaded in when I compile my program. So I guess my point might be that I really want to save something. I want that label there because I might go to some other function, BL, some crazy function, and maybe in the crazy function, which is going to be defined down here somewhere, some crazy function, we are doing some stuff like load R0, put value of a sensor into R0, store R0 in do some other crazy stuff. That's the end of a function. So I haven't explained how functions work yet, so just bear with me. But like, you know, our code isn't always an obvious stream of instructions with an answer we already know. Like if I ask you to write a program to multiply 9 and 6, 9 times 6, well, why not just enter the answer into your memory, right? There's no particular reason not to do that. If you want to just skip the multiplication, you could just enter 54 into memory. But the point of the program is to demonstrate that you know how to multiply numbers that you might not know where they're coming from. So in a bigger example, the input of something that you're storing in memory might come from a sensor, right? It might be something that a user is entering on little buttons. So you don't want to just store it directly in a register. Another good example, if we're not dealing with sensors, is your data could contain, ASCII. Here is an incredibly long sentence. I really don't know when it's going to end. How about I write a little bit more now? Full stop, a bit more ASCII. Wow, the text is just continuing. I don't know when I will stop. So, wait a minute, how many bytes did we have to store in registers now? 64. So I think I've written more than 64 characters in ASCII text here, and each ASCII text character takes up 1 byte of storage. So I've just blown my budget of registers. So if I want to write a program that does something with this text, I'm going to have to use memory, and I'm going to have to use memory addresses to find it. If I just delete that word, I'm going to see if my crazy fake program is going to build. I might cut out my memory, my fake crazy function there. I'm just going to load 1 character from that memory in a register. I'm going to jump ahead in the course a little bit right now, but there you go. Load R0. This is going to be the address of that first bit of text. Let's have a look at our memory. 0x20000000, and I want, OX 7F, 128 bytes of memory. There's all my text is encoded in there in hexadecimal format. There it is. The memory reading function has given me what it is in ASCII, which is handy as well. Here's an incredibly long sentence. I really don't know where it's going to end. How about I write a little bit more now? Wow. You can see I've got 2 ASCII sentences. One of them is on 1 line. I should have put a space at the end of it so that it has a space there, but it doesn't. There's no way I'm going to store that text in registers. It's just way too much. And how would I even know, is R0 going to contain the first 4 bytes and R1 the next 4? But then I need my registers to do stuff with it. What if I want to do something with that memory? Well, I'm going to have to load it into registers 1 by 1. I can load in the first character, which is OX48. That's a capital H. OX48 is a hexadecimal character. Now, what if I want to go through my text and do something? Well, I might have do something with that first character. Then I might say mov R1 0 text loop. I'm going to make a label there. I'm going to increment my text loop, my R1, add R1, R1, 1. I can delete first because I'm going to go through all my characters. Be text loop. So I load my memory address. I load up 1 character of memory. I've got keeping track of where I'm in the loop, and I'm going to offset by R1. I'm talking about offset memory, memory and offsets instructions in more detail next week, but here's an example of it. This is going to be load memory addressed by R0 plus R1, and I should load it into R2, shouldn't I? So I'm not overloading R1. do something with that character. Don't know what to do. Something good. I'm running out of time now, but I just want to show you why you absolutely do need to load memory addresses and not just data into your programs. I hope this works. I just invented it on the spot. It was a good idea. So the first thing I'm going to do is load up that memory address. I probably could have done that outside my loop, so I would save an instruction each time. I'm going to load the first byte into R2. That's 0x48. Increment R1. Go back to the loop. And the next byte, 065, that's this one. Then the next one, etc. 72. So I can go through my text character by character with this little loop and the letter byte command, which is pretty cool. No other questions? I think hopefully everyone is very impressed with my little text reading code. Did you do .ASCII in labs already? I have a feeling you did. So hopefully you did. I might call that a day and we can talk more about memory addresses and memory space where no one can hear you scream on Thursday. Folks, it has been a lovely afternoon to spend talking about memory addresses with you. I'm going to call it the end of this lecture. I'll see you folks on Thursday. Have a great time in labs this week and let me know if you have any questions on Piazza. Until Thursday, catch you later.